Today we have a topic Gaussian mixture model. As the name suggests, Gaussian mixture model, it means we are talking about the model that is to be followed by the Gaussian distribution. If we're talking about the SOM or expectation maximization algorithm, so these two approaches or algorithm are supported by its own fundamental part. So if we're talking about the SOM required to prerequisite part about the neural network. When talking about the expectation maximization, so you must be known about the basic fundamental part, and that is the hidden variable and observed variable or unobserved variable. So in the sense we have seen the latent variable of the data set in the case of the EM model, or we can say the expectation maximization algorithm. After that, we have another model, and that is the Gaussian mixture model. From this model, we need to understand the step properly, and this model will describe how it is well suited or how it is well defined model than the Kmeans clustering algorithm. In the Kmeans clustering algorithm, we have a lots of the drawbacks, but we didn't touch those parts. So now come to the point, that is GMM, that is the Gaussian mixture model. So if I'm talking about the Gaussian mixture model in detailed manner, so just let us understand the first drawback of the K-means clustering algorithm. Okay, so I'm going to start my lecture by describing the drawbacks of the K-means clustering algorithm. Then you will understand the concept properly over here. While discussing the K-means clustering algorithm, we found that, or we feel that our clusters are just look like as a circular formation, because in between what part we are selecting, that would be represented by the centered and other data point which will be connected, and we will choose all those data points which are close to the center, and they will make a form, and that form just representation would be like as a circle. So this is a picture we have in our mind that is to be followed by the K-means clustering. But is it really every time you will get the same thing? No, because something is depend on the data set. So from that case, when you are not forming your circle representation of the cluster, then at a time we are saying to over here, we are not getting the good accuracy. And to about the such thing, and to get or to manage all those things, we have a model that is GMM model. So before jumping the GMM model, just let us understand once again the drawback of the K-means clustering, and it is written over here. K-means is a good algorithm, no issue, but we have noticed, and you will notice that the clusters are represented by the circular shape, and we have already done. So this is the reason, because we have chosen the centered value. From the centered value of the cluster, we will decide the edge distance followed by the equidistance, and we have just managed by the everything followed by the mean value, and it is a iterative process we have done. So without wasting much time, just let me show the my next image, and this image will show the proof to justify my answer. Now let me know the status, the visibility of this image is visible to all or not. So just let me know the screen is visible, the image is visible to all, and which is to
Yes,
be plotted,
yes.
yes, right. Which is to be plotted by the three different colors. One is a green, blue, and orange. Can anyone tell me what is the drawback you are having right now? If you are plotting the data point to representing the cluster by the K-means clustering algorithm, so what is the drawback you are observing over here by this image? Theoretically we have seen, but by the this image, what you are observing? Can anyone tell me? Can anyone tell me what is the drawback we are observing? Anyone, please, you can speak over here, no issue. If you don't know,
Sir,
no
I
issue.
think there is a overlapping of data.
Yeah, this is a good and brilliant point. First one, and other one who want to speak something, please tell. Anything? Anyone who want to speak something about this image? What you are observing? That is a good thing. You have been observing the good right track, but any other student who want to share other idea, please you can share. Okay, no problem. I will tell you. See, definitely the student observed the right track. What he or she is observing over here, it is good. So the other student may also be observing, but they are trying to speak over here, no issue. If you try to make a cluster of a data set, and which are to be represented over here in form of the non-circular representation as we have seen into the about K-means clustering. So we try to solve a problem with having the K-means clustering. Then you can observe over here we are overlapping something. Something means data points. Some data points are overlapping. They may overlap 100%. They may overlap partially overlap. They may overlap 80%, 20%, 70 or 75%. Depend on the part, how much part of they are overlapping. But the question is, we have K-means clustering algorithm itself is exclusive clustering, and in this case, the data points should not overlap. If they are overlapping, that would be the part of the example of the overlapping clustering. So K-means clustering is not a overlapping clustering example. It is a partitioning clustering example. And how you can say or how a data point can make overlap, that is the biggest drawback of the K-means clustering. And to avoid the such thing, we have a beautiful term that is the GMM, that is the Gaussian Mixture Model. So to avoid the such thing or to overcome that problem, we have introduced a new model that is the GMM, that is the Gaussian Mixture Model. So every lecture in the every lecture in the every class, you will find that there will be sequence, there is some prerequisites you must know. So if you don't know the idea of the K-means, then you will not able to understand GMM. That is the point. So we are stepping the GMM concept. We are taking the GMM step from the our previous concept that we have seen the K-means clustering, and that is the point. So from this point, you have been observed over here, and just I'm also observing over here, and you can just found the simple concept. Some data points are overlapping. Okay, so from this point, I'm marking. See here, orange and green data points are overlapping. Some not 100%, some percentage. You can just please observe. Okay, and here please observe. For a betterment, I can make it a zoom mode so you can understand with the magnifying part. See, now it is visible. Just see, some parts are overlapping of the data, and that is a not good way. So that is a drop. Okay. So from this point, we have to introduce Gaussian mixture model. So now let us understand what is the Gaussian mixture model. So Gaussian mixture model assumes that certain number of the data points which are plotting or which are distributed for making the cluster, all distribution will be done by the Gaussian distribution, and that is also known as the normal distribution. So from this point, we will understand the Gaussian mixture model. So here we will represent the our cluster by the distribution of the data point followed by the Gaussian distribution model, or we have the normal distribution. So now question we should have in our mind, what is normal distribution? The normal distribution is a probability distribution mechanism, and it is also known as the Gaussian distribution because it was first discovered by the Carl Friedrich Gauss. So based on the name of the mathematicians, the name of this model given here, the Gaussian distribution, and for this parameter, for this concept, if you try to plot all the data point on our graph, then we are following the Gaussian mixture model, and definitely this point we need to keep in mind. Now, if we're talking about the normal distribution, so how normal distribution will look like, we will see this part. Okay, so let us move to the next slide. Then you will be able to understand something over here. So here, if you just look at here, we have the blue, green, and orange color. So if I'm speaking about here, then you have been observed there are three clusters are over here, and these three clusters are represented by the or plotted by the over here in form of the K-means, but they are just representing like they are plotted in form of the Gaussian mixture. So we can plot all these data points by using the Gaussian distributions, like we have seen into the previous slides, and which is put by the three different color distribution. So distribution just look like as a Gaussian distribution. So let us understand these three Gaussian distribution. We have GD1, GD2, GD3, and its mean would be the mu1, mu2, mu3, and itself. Variance can be identified by the delta 1, delta 2, and delta sigma 1, sigma 2, and sigma 3. So sigma 1, sigma 2, sigma 3 are the variance and means values of respectively we can see. So in the Gaussian distribution, we have a two term that we are using right now, mean and variance. But when talking about the K-means, we already discussed we are using the mean. So we are approaching the one new thing, that is the variance from the mathematical part in the Gaussian distribution model, we can see the Gaussian mixture model. So from this point, how we can calculate the mu? So from this image, you will able to understand if in a circular way, if data point we are selecting and we are just representing itself in just form a circular, and that is example of the Kmeans. We have just noted down. So mu1, mu2 are just some mean values of the its clusters. So definitely we can understand this concept, and we have already seen this concept right now. And that is the starting point of the Gaussian mixture model. So with help of another example, I'm showing the my proof over here. Now let me know the status from all the people right now. Is it visible to all? This screen, this image is visible to all. So I'm just maximizing right now. Just tell me, the screen is visible? The image is visible?
Sure.
Yes, sir.
Okay. Okay, so you can observe there are three different kind of the cluster I'm plotting over here. We have a green, cyan, and blue. So if I'm picking the any color data point, then if it is purely colored by, not mixing, it is purely colored by its own color, respectively clusters definitely. So if I'm picking the cyan color, so you can observe over here, I have picked it over here and marked by the circle. And blue I have chosen over here, and green just at the bottom side I have chosen. So what you are observing over, see here, green. So they are pure belong to the same cluster. But here we have some drawback. What is the drawback? Here you can observe over here in between. Just look at the in between middle point. So let me show my proof right now by the plotting the this portion by the green color. Okay, so yellow color. Yes, this one. And now let me show here. So from this portion you can see here blue and cyan color are representing by the one single data point. It means the particular data point are sharing its own identity to different cluster, and that is a drawback. It should not be in the K-means clustering. And if it is happening, then we need to divide. We need to differentiate. Either it should be the blue color cluster or it should be cyan color cluster, and that is to be handled by our simple model, that is the GMM. So in the GMM, what we have, we will not distribute the data like in form of the circular representation. We will representing the data by the Gaussian distribution or normal distribution. And from this point, we will understand how we can understand. So let us understand this part right now. Now, this is the part. So what you are observing over here, just theoretically, you can just theoretically, I'm not reading the necessary point. Just we need to understand the concept right now. So from this point, you can observe over here, if I'm picking any color of the cluster, so I can say the particular color value identified by the its own data point. So such a data point just contain the probability 1, and rest of the probability of the other cluster would be 0 by default. So just let me explain this example right now by over here. Just let me choose a different color value, then I will tell you right now simply. See. Suppose I'm choosing the this blue color point. So what is the probability of the blue color here? So here, if suppose there are 3 clusters, so blue, cyan, and green. So the blue probability will be the 1, and other probability would be here 0, and that is the point. Same thing, we need to go for the this green color. So but choosing these two data points, these two data point will contain the green color probability 1 and other color probability would be 0. Then we can identify it by the this one, because it totally separated. But when case of the in this case, when we are having the overlapped data point, so in this case we are observing over here. If blue ratio is more than the cyan, so we can say the its probability will be distributed between the both clusters color. So that is the point we need to keep in mind. Green probability will be 0, but blue and cyan probability we can calculate it by the its number of the ratio for sharing purpose only. So suppose blue is sharing the large volume, so we can say the 60-70%, or we can have the probability. But here it is written over here, the blue is just sharing the minimum portion of the particular data point, so we can say it is a 20% probability. but 80% probability will manage by only the chance. But this data point is overlapped, and that is should not be into the our part of the K-means clustering. And to overcome this problem, we have to understand the GMM. Okay, so this is the introductory part. We have seen what is mean by the GMM and why GMM is required. So any doubt over here? So far we have discussed. Any doubt? Please, you have any doubt? You can ask me right now. Any doubt so far you have? Please, you can ask me right now. Just tell me any doubt you are having right now.
No doubt, sir.
Okay. So now I'm going to the next slide to explore the more detail about the GMM. Now, if I'm talking about the Gaussian Mixture Model, and I'm saying over here the Gaussian Mixture Model, the data distribution will be represented by the Gaussian distribution, just like the normal distribution. So you can see over here, if we have the 1, 2, 3, 4 different color cluster. Okay, so I have already marked by the one line that is over the graph. You can see one line by the highlighted pattern. So it's showing that it has the sub values. And the point I'm just coming, just let us understand the beginning part right now. So green color, orange color, and red color, we can say the blue color. These are the different kind of the values we are having, and these values will be identified by the clusters. So and they are representing the graph following by the normal distribution or Gaussian distribution. And now we have seen and we have understood the what I mean by the Gaussian model. So distributed distribution will be done by the Gaussian distribution, normal distribution. So graph will be represented by like this. So mu means mean we are, suppose I'm choosing the blue line. So mu we are getting over here 0, but its variance we are getting that is a 0.2 or 20% we can say. Same thing, mean we are getting 0, 0, and for the blue, for the red and orange line as well. But its variance we are getting the 1.0 and 5.0. So you can observe over here the variance of the orange line we are getting the highly, that is the 5.0 compared to the other one. So that line I have highlighted over here. So it shows that the few data if I'm using for distribution by the Gaussian distribution, then we are getting the mean and variance. So higher variance values we are getting, that should be represented by the our data is spread in large volume. And data is spread in the large volume. Okay, so that is the point we need to keep in mind because it covering the maximum portion. And now the well shape is just defined. Now this diagram is just represented by all these diagrams represented by the well shaped curve. So the curve will be represented by well shape. So blue, so I'm coming on the blue. So blue line you can see, a blue curve you can see right now, well shaped blue curve. Is to start by the after the -2 and then started by between the range -2 and -1 and ended by the 1 and 2 range between. So and the rest of the part will be as a 0. But if talking about the orange color, then you can see it's started by the -5 and touching the 5. So its clusters data points are spreading in the large volume. And from this point, we will understand some mathematical will be required. And why which we are getting this the point, the variation. The variance of the data points describing the detail, the how the data, the particular cluster is spreading. So how data are spread, how data points are spreading into such cluster that can be identified by the variance only. So means we are using for the calculation purpose, and with the help of the means we will get the variance. But finally, we are observing something here that is the high the high value of the variance will determine that your data is spreading in the large volume in such cluster. So that is the point. From this point, we need to understand the next part right now. Now this one. So cluster 1, cluster 2, cluster 3, we are showing over here. And we are calculating the three different variance and mean. You can observe over here mu1. Mu1 is the mean of the red color cluster, and it has its varies mu sigma 1. Same we have the mu2 and sigma 2 and mu3 and sigma 3. So from this portion, can you tell me which data point is spreading in the large volume? Can you tell me? Can anyone tell me? Which data point is spreading in the large volume? Can anyone tell me? It's
Sir, can you repeat your question?
I'm asking which cluster is spreading the data in large volume, by which we can determine. So with the help of the mu and with the help of the variance, you can define. So can you tell me which cluster is spreading the data large volume? If you compare the blue and green, so green is not spreading in the large volume because it is covering the limited amount of the some specific range only. Red and blue we can cover, but by the observing the blue and red, you can say the blue is just covering the large spreading area. Don't think about the size actually. Okay, we need to see its variance. Based on the size of the base of the value of the variance, we can identify. Because now you can observe over here. Now see, this is the just here we have the its variance value. Okay, we have the this value. So what is the value of the variance we are getting over here? That is more important, by which we can decide that how much data are spreading. So mu1 and the sigma 1 sigma 3 we can compare, and by which we can get sigma 2 is just showing the minimum value compared by the sigma 1 and sigma 2. So variance of the cluster 2 is not good, but cluster 3 and cluster 1 we can compare to decide which cluster is spreading the data in large volume. So from my perspective, you can observe blue could be, or red cluster could be. So this could be the example of your normal distribution by which we can identify the something, that what is something. Something means it's mu, it's mean, and it's variance. Okay, so this is just idea about the Gaussian distribution. Just let me know the any doubt you are having, so I can explain once more, or now this part is clear. Or anything you want to ask right now, then please you can ask me. Yes, speak something so I can continue, or I can explain once more.
Sir, how did we select that red line and the blue line that we discussed in the previous slide?
This one you're asking? This one you're asking?
Yes, sir.
See, my dear. Here we have the three different wheel-shaped curve of the each and every cluster. Suppose in your model you have a one cluster. Okay, I'm choosing different color for explaining purpose for you. Suppose now you have a one cluster. Okay, and its mean value we are getting something just like something. What is the value? So we can decide the value only the 0 and 1. Okay. From the 0 and 1, can you tell me the what is the mean you are expecting? What is the mean of this any x cluster you are looking for? What is the mean? Can you tell me any range? Can you tell me any value?
Sir, 0.
0 point
0.8.
0.8. So this 0.8 you have chosen. That is what? That is the it's so it could be around like this one. Okay, so and the distribution of this data plotting just like minus 3 to plus 3. Okay, that is the point we need to keep in mind. The distribution should be in equal way, and this could be the, suppose we have the, this is the center 0. So we can make this plot like hardly this one. Okay, and like hardly this one. Okay, I'm not able to make the proper way, so just for understanding purpose. And that is you are getting the mean, that is you are getting the 0. Suppose you are getting the its mean 0.8. So 0.8 you are meaning getting the mean. So that should be not that should be 0 and that should be 0.8. That should be 0.8. Okay. And if you are getting the width variance, so you have to calculate what are the data points you are plotting. And this should be -2 and this should be -1 and that is 0 and that is a 1 and 2. This is a +3 we are. So from this point the value we are picking, that is your 0.8. So from this point you are getting the its mean 0.8 and you are getting something like variance. Maybe you can get the variance positive, negative. So you are getting the positive or negative variance, and that you are getting the variance from this mean to this variance. That value is known as the variance, and that is to be represented by the sigma square. Okay, that is to be represented by the sigma square. Same thing here. We have the three different kind of the example of the cluster 1, cluster 2, cluster 3. So from this portion, you can see the its spreading is going the more and more. Now see. It is not just like ended over here. It is spreading and covering the more and more range. Just like example this one, I'm just representing the same thing by another example. See, it is touching by the -4, -5 as well. Suppose so, it just look like this one, and suppose it has like this one. So suppose its mean is around 0.7 or 0.5 something, 0.5, 0.6 something. So its mean would be 0.6 something. So it could be around like this one, 0.6. Okay, let me remove this point right now. Yeah. And it is covering by the maximum range. Why? Because it is also following the 4 and 5 as well, and its range is starting by the -5 to -5 to +4. So its spreading will be high. So in this case, the variance will be high. So that is the point we need to keep in mind. So there's no guarantee. There's no guarantee based on the its mean we will decide. We will decide the spreading of the data point based on the variance. Another example could be like this one. Suppose you are covering like this one, and it is having the one. It is having the one value of the mean. So it could be followed by the like this one. So there is maybe some different example. So it can have the one. So that is the point we need to keep in mind. But what is the covering of the maximum data point that is to be decided by the variance, and that variance will be applicable into our Gaussian mixture model normal distribution. So normal is the measurement criteria how we can measure the our normal distribution on these two factors. One is the mu, that is mean, and sigma, that is variance. And so here we have the example of the various cluster like this. This is the example of the what these different color clusters. So it is plotted over here, and we are showing by the our different clusters. From this point, we can say no, this one cluster 1 or cluster 3 could be spreading the lots of the data. That is the point. If you ever justifying the last statement, just remember that higher the value of the sigma value, more would be the spread. Okay, so it means number of data points are covering that part. That is the reason. So now this point is clear.
Yes, sir.
Okay. Now, so in one dimension space, the probability density function. So here we have to keep in mind some theoretical purpose. We have to keep in mind some equations only. So how we are getting and how we are representing. So please keep in mind sigma square we can write over here, but it is not sigma 2. Sigma 2 is not is the name of the variance, sigma square. Huh? Okay, please keep in mind. So in a one dimensional space, the probability density function of the Gaussian distribution. So if talking about the Gaussian distribution, if I try to use the probability density function in one dimensional space, okay, and just like this one dimensional space, how we can define the one dimensional space? This one. All the data points are plotting by only the our one one axis, or we can say no other axis will be involved, and that is to be represented by the linear representation. So density function of the see uh, the distribution will require the probability density function to determine the its values. So Gaussian distribution will be used by this equation, that is the fx mu sigma square. So that is the point we are what we are using. We are using the mean and variance to determine the our probability density function of a Gaussian distribution in case of the one dimension space. And here the formula will be the 1 upon root uh, root 2 pi is mu square, and e to the power inside the bracket 1 minus mu whole square divided by the 1 upon sigma square. So where is the mean is, again mu is mean, and the sigma square we have the variance, and that is to be done by the this part. But in the case of the see, if you remember the example as I told you once again, in the age and annual income, we have made the we had made the cluster of the general income. So overall representation will be done by the one dimension only. Okay, that is the point. So at a time, suppose you are using the such data point plot, you are using so those data point for plotting purpose, then Gaussian distribution formula would be this one. But when talking about the some data representation by the 2D manner, so how we can represent. So 2D data can be represented in simple way, but if you want to represent your data in the 3D manner, then how you can represent? So 3D representation will be represented by the 3D graph. So there are so many approaches by which you can show. You can show your show your result. You can distribute data properly. So at the time you are using the 3D diagram to represent your approach in the 3D manner, and then the diagram is known as the 3D bell curve. Okay, so over the slide you can see the example is the best example of the 3D curve. 3D bell curve. So by default over screen I told you this is an example of the 2D bell curve. Why? Because we can identify the x-axis value what we are getting and what is the value of the y-axis what we have. So based on the x and y value we can represent the our bell curve, that is 2D bell curve. And in the 3D we can use this graph. But the question is not ended so far here. But when we have any data point which are required to represent by the 2D plane only, okay, so 2D surface. So at the time you are required to have the something better way of the probability density function. So how we can calculate the probability density function? So here we have this formula, and keep in mind this formula. So these are the standard formula. But what we have introduced over here, the new thing we have over here, that is the summation. So x will be definitely the our input vector. So what is the input vector I'm speaking about? It means we are talking about the features, input features. So what is the feature we have? So feature could be one feature, two feature, many features. So based on the features, we will decide the its 2D mean vector. So 2D mean vector will be represented by the mu, and summation will be the 2 by 2 covariance matrix. So covariance matrix will be the 2 by 2 matrix. We have to keep in mind it's a standard. Why 2 by 2? Because our surface, we have the 2D surface, which is to be represented by the x and y. So covariance matrix should be 2 by 2 square matrix. We have to use as it is. That is the point we need to keep in mind. But when you are using the data represented by the 3D manner, then your covariance matrix will be automatically 3 by 3. That is square matrix, and that is to be used by the 3D model or a 3D bell curve at a time. But here, how we can use such values, that is to be represented by over here. X is the input vectors, and use the 2D mean vector, and summation is the 2 by 2 covariance matrix. That is a square matrix we have to keep in mind. And covariance would be now define the shape of the curve, and that is the regency. Covariance matrix we are using, and due to this approach, we are making the well curved shape of the our distribution, and that is the point we need to keep in mind. And if you are having the multivariate Gaussian model is saying to us, suppose you are looking for the 4 by 4 Gaussian model. It means what you are having. It means you have the 4 input features, and based on 4 input feature, now you are calculating the 4D mean vector of the mean. Then now you are going through the summation. So your square matrix for the covariance would be the 4 by 4. So here d into d covariance matrix is written, which is marked by the circle over and the red color. It's showing that we are discussing about that if you have the n dimension. So on basis of the n dimension, your 4 matrix size would be the square matrix. So n into n or d into n, d means dimension, total number of dimension. That is the point we need to keep in mind. And based on that parameter, our input to vector, and mu vector will also be updated. And from this point we have to use. So these are the already standard defined equations. We are not any right to change its basic fundamental thing. So we will add up all these equations for the solving purpose. This is the probability density PDF function, that is the probability density function to determine the values. Now where we can apply, that is a good question. Where we have the values, now look at the diagram. 0 to 1 value we are defined. So what is the value? What is the value that is to be plotted? We have to mark for drawing our 2D curve, 2D this 2D or 3D bell curve, that is defined by the probability density function. So when we have only the single dimension, then at the time this probability density function we have to pick, as we have to pick this function. So in this case, we have to use a covariance matrix rather than the covariance. Okay, rather than the variance, we have to use a covariance matrix. So in the 1D dimension, variance is sufficient. But in the covariance matrix, ultimately we are using the variance. So practically or mathematically, I can prove over here, but I can say in the K-means, we are using only the mean. If you remember that mean, we are using only. The calculation for the mean is going on. Nothing else we are doing except to the mean. But in the case of the this portion, what we are discussing, that is our important point, Gaussian mixture model. You have been observed over here the mean and covariance or variance we are using. So one additional mathematics we are using to justify our work, and why it is required, because we are here we have the data distribution in the form of the Gaussian distribution, normal distribution. So variance will be applicable for measurement purpose. So covariance matrix will be applicable, and that is the reason. So we have the important aspect covariance or variance, and due to this nature, we can say the data plotting what we are looking for, that should will not be overlap at any cost, and that is the biggest reason for using the GMM model. And what is the drawback we have seen, and to overcome such problem we have a GMM model. Okay, and there is summary. This is a summary I will tell you, but the point I was discussing is the point actually. This summary I am speaking right now, but I will come back to the 12 to other more concept right now. So now K-means only consider the mean to update the centroid, while GM takes into account the mean and variance of the data, and that is the reason for using the GMM. Now this point is clear. Why GMM we are using? Just tell me right now. Any doubt you are having?
Also clear.
Okay, so the point we need to keep in mind, if we are trying to solve any problem, so why we are using such concept, that is the important point. So we start our topic to understand what are the drawback we have taken. Now let us back to the some important point here. Still we should have a question. So you are saying the mean and variance you can use in the Gaussian distribution, but what is the important criteria by which we can assign the mean and variance to the our model, Gaussian mixture model? So in the Gaussian mixture model, what is the important method by which we can assign the mean and variance to our data point? And from this point, we have a term that is a EM. And EM we have already discussed what is that, expectation maximization. So expectation maximization approach will help to assign the mean and variance to each and every data, and from that point we will calculate. Okay, so don't worry, we will see this part. And that is the reason expectation maximization play important role to assign the mean and variance to our GMM model, and that is a special reason. So now we have already discussed the expectation maximization model, so no need to discuss more. And see, this is the reason. Now, that is the reason I told you before GMM, I told you about the expectation maximization. Now, so how expectation maximization involved into the GMM model, and that is the point we will understanding right now. Because we are touching this part right now, so let us understand some more detail about the important rules of the expectation maximization algorithm into the GMM. So now let's say suppose we have the number of the clusters. How many clusters? We have the k number of the cluster. Okay. So we're talking the k number of the cluster, then total number of the mu will be mu1, mu2 up to mu k. It means if you have the 5 clusters, the total number of the mean would be the mu1, mu2, mu2, mu4, mu3, mu4, mu5. Same thing, we have to calculate or we have to determine the its covariance values by the matrices, of course. and those will be identified by the k value or kth number of the cluster, sigma 1, sigma 2, and so sigma k. And suppose we have the 5 clusters, so sigma 1, sigma 2, sigma 3, sigma 4, sigma 5. These 5 would be about the covariance matrices, and that is the reason. So we need to keep in mind. So from this parameter we have to do. So there is a point we have to keep in mind. If you want to distribute and if you want to define the number of points for the distribution, then the density between the each and every distribution we can easily find out by the our mathematically proof idea, that is the pi. So with the help of the pi I, we can represent I means number of the data point value, total number of data points will start I to n. So from this point we will start. So what is the expectation maximization? So we have the two step, one is E step, other one is the M step. So now let us understand this point right now. E step. So what is E step in the expectation in the Gaussian mixture model following by the expectation maximization model? So what is the E step? E step is nothing, just it's saying to us you need to calculate the probability and that belong to the cluster, and this cluster it means RIC. RIC means right right cluster, actually right cluster toward the our data point. RIC means right cluster toward the ith data point. I'm speaking once again. RIC means right cluster toward the ith data points. We are plotting the, we are expecting, and here this is a step expectation step. So probability xi belong to the C is for cluster, and divide by the sum of the probability xi belong to the C1, C2 up to the CK cluster. So we have the we must have the total number of the cluster. I am speaking about, suppose we have the 5 cluster because we have decided. So we will choose the some probability, that is C1, C2, CK for the each and every clusters we have. So C1, C2, C3, C4, C5 would be the probability of the cluster, actually probability of the cluster, which is to be calculated by the data point, that is xi. And from this point we need to determine the right cluster toward the our data point, and that is to be calculated by our simple formula, probability xi, probability of the xi belong to the C cluster, and now it divide by the sum of the probability xi belong to the C12, C2, and so on, so CK cluster. If this value is high, suppose we are getting the high value, so it means we are getting the right cluster, and otherwise we are getting a low cluster, so it means they are not getting the good cluster as we have decided or as we are expecting. So in the program, in the solution, we will decide some benchmark, and from that benchmark or that threshold value we will decide that it's high or low value. So it's up to you what the parameter you will decide, but we will not decide this by the manually. The algorithm has a right, or the algorithm has a fundamental concept internally and decide automatically some threshold value and decide the your point. So how we can decide, and that is to be done by the clustering we have already covered. To the centered, and again we need to determine the its mean and so on so stuff. So by this approaches, it automatically decide the threshold values. But when talking about the expectation maximization is saying to us after the or post each step, we need to back and update the pi value, mu value, and summation value. Okay. So if you want to update the pi value, this pi value means density, actually. Pi means density. This density defined that how many data points belong to the such cluster. So suppose out of the 5 cluster, you have chosen the 5 cluster, and out of the 5 cluster, if 3 data points belong to the cluster 1, so that would be your density of towards the such cluster, and we can define that value by our mathematically pi. So here pi will be equal to the number of the points assigned to the cluster divided by the total number of the points. The total number of points, suppose we have the 5, and a cluster we have decided 3. So in a cluster 5, total number of data point was 5, and only the mapping will going into the only 3. So that would be we have over the 3 by 5. So that is your density. By this approach, we will decide the percentage of density, and from this point, we will update this process in iterative process. So this is what this is a maximization. So we will try to maximize our cluster size, we will decide our data point for the respectively cluster maximization way. And if it is not so go on, so an iterative process will go on, and we need to update the right cluster to what the ith. We will update this word again this step, and until we will get the data point to the right clusters only. So right cluster, how will decide the right cluster? Based on the its maximum value. So they are if you are getting the RIC value in the maximum, so we are choosing the right cluster, else we are going to the low cluster. If we are not getting the right cluster, then we need to update the M step. And if after updating the M step, we need to update the other values, mu, mean, mu, that is mean, and covariation matrix, that is summation, we have to do update. And this again, this would be a iterative process, just like the our expectation maximization algorithm. So this is the required portion, and and then mu will be updated by this formula, and cluster of the covariance matrix cluster will be updated by this formula. So these are the standard equation situation formula we have to use. We have to keep in mind. No need to change this portion right now. So these steps are saying to us at each and every level in the GM model, expectation maximization will be the implicit method that is required to solve our problem. Okay, so that is the reason. So this is the reason. After this point, no need to explain the expectation maximization. But if I taught you this algorithm, see, I already taught you this algorithm. So if I'm teaching this method, that is the EM method. So where it is applicable and where it will be helpful, only in the case of the GMM, it will decide the mean and variance in better way. And that is the reason we will use the EM approach EM method. And that is the reason. In this case, we have used, and how we can use. So we are help of these standard equations we have to use. Nothing we will not change. We have to adopt all these equations as a challenge, as our solution. And somebody is saying to us in the Kmeans we have used only the mean, but in the GMM you have been observed, you have used the covariance, you have used the mean, and you have used these two important concepts. And with the variation, you will decide where it will jump or where it will go. Where means who will go on which is going to movement. Data point will have the right to move. Data point has the it's shifting. We're talking about the data point. They can shift, they can adjust it. Okay, so this is a theoretical portion right now. So any doubt in this portion you have, please you can ask me.